All right, so I'm just going to just so it choose the correct one first. So what's this asking? So rotation about 90 degrees. What are the coordinates of the points after? But okay, so I see what they're doing. So you got a lot of different tasks here on this question. It says draw triangle LMN with vertices 2, -2, M at 5, -4, N at 4, 4. Find the coordinates of the vertices after a 90-degree rotation about the origin, and then about each of the points L, M, and N. Okay, so that becomes a little bit more tedious when we look at that second part going around L, M, and N. So I'm going to cut this out and do it over here. All right, so remember our rotational rules is that if I take a rotation of 90 degrees, okay, and it's about the origin. So a lot of times they'll say like R and then a subscript of 90 degrees, comma O, or they might write comma origin at the bottom. If we're doing that, you start with a point A, B. You guys remember it turns into you flip the ordered pair, and then you negate that one. That make sense? Okay. So when we start with L, M, and N, okay, so L is at 2, -2, M is at 5, -4, and N is at 4, 4. Okay, to get L prime, you're going to flip these, so it becomes -2, 2, and then you negate the first one. So negating a negative turns it to a positive. Then if I'm going to do M prime, I flip them, and then negate the first one. So it turns into a positive. And then the bottom one, and then I'm going to flip them again, which it doesn't look like I flipped them, but I did. And then I make the first term negative. So that's how we rotate around the origin, okay? Now, in the other parts, when I want to rotate 90 degrees around point L, okay, then that is more difficult to do because we don't have a rule to rotate around point L, because point L is just some arbitrary point, 2, -2. Because L could be 3, 5. It could be -12, -15. So there'd be a different rule for each one of those, right? Does that kind of make sense? So what we do, and I'm going to draw just a quick sketch of this, and we'll do, maybe do 1 or 2 of these, but L is at 2, -2. So there's L, okay? We are going to make L become 0, 0. Okay, so if L becomes 0, 0, then this point here, which was at 5, -4, which is M, so 5, -4, which would be right there from the real 0, 0, is actually 1, 2, 3, 1, 2. It's 3, -2 from L. Does that make sense? Okay, and remember what we did with that, and the way I can find that is I basically take my original point, and then minus the point of rotation. Okay, so my original was 5, -4. 5, -4. I'm going to subtract out my point of rotation. My point of rotation was 2, -2. So what's 5 minus 2? 3 right there. What's -4 minus -2? -2. Okay. Then we'll do the same thing with N. So I go 4, 4, and subtract out 2, negative 2. So 4 minus 2 gives me 2. Okay. So from here I'm going to go right 2. Okay. And then 4 minus negative 2 is 6. So I'm going to go up 6. 1, 2, 3, 4, 5, 6. So it's that point there. Okay. So we said 2, 6. So that ordered pair and that ordered pair are based off if that was really 0, 0. Okay. Now that we have it, now that these are structured off of 0, 0, okay, we can apply this rule to them. We can flip them, so it becomes negative 6, 2. And this one's going to become 2, 3. So I'm going to circle them just so I keep track of which ones I've got. So those are now rotated around this 90 degrees. Okay? Now what we need to do is add back in the point of rotation to both of them. So add back. So if I started with negative 6, 2, start with negative 6, 2, add back in 2, negative 2. If I started with 2, 3, add back in 2, negative 2. So it's negative 6 plus 2. Negative 4. What's 2 plus negative 2? 0. Okay. Now what's 2 plus 2? And what's 3 plus negative 2? Okay, so this would be M prime, this would be N prime. If I'm rotating this triangle right there around L 90 degrees, isn't L prime just going to be 2, negative 2? Stays on itself, right? Just to demonstrate this, so I'm not going to go through another. We're not. The question asks you to do it. It says then go to M and rotate the figure 90 degrees around M, and then do the same thing for N. Okay, but we should be able to, and this is why I haven't forced you to work a lot with GeoGebra on your own, but my hopes are that maybe some of us are, and this is one of those reasons why I would like to maybe be able to do this. If I go 2, negative 2, plot that point. That's L. Okay. And then M was at 5, negative 4. And N started at 4, 4. Okay. So these are the 3 ordered pairs that they're talking about. Let's say that I want to rotate. So I click on the rotate option. I'm going to select this thing here. And then click on L because that's the point I want to rotate around. I want to go 90 degrees, and I want to go counterclockwise. That's always the rule. If they don't say, because I don't think in the problem they set a direction, then it's assumed counterclockwise. Hit OK, and now let's look at those ordered pairs. L prime was 2, negative 2. We said that was the same thing as L. M prime, did we say that was 4, 1? Okay, and I think maybe I mislabeled something, but regardless, you get. So I think I mislabeled these, but 4, 1 and negative 4, 0. Those are the ordered pairs of those rotated coordinates. It kind of makes sense. When you're doing, and this is holistically for dilations and rotations. If it's not, so I'll give you some kind of quick instructions here. If not rotating or dilating around 0, 0, then this is what you do. You take your original points from the pre-image, and you subtract the ordered pair of rotation or dilation point. Okay? So that's going to give you, and that will yield an ordered pair that you can use dilation and rotation rules on. Which, as an example, if I were to take like a dilation of, I'm just going to say K, where K is just some value, might be 2, might be 3, might be a half, whatever, of AB, then when I dilate, that ordered pair becomes A times K and B times K. If I'm doing a rotation of 90 degrees, then AB becomes negative BA. Okay, and there's 3 other rules that we learn, or 2 other rules that we learned for 180 and 270. But after you subtract your original, start with the original, subtract from it the ordered pair of rotation, you're going to get a new ordered pair. That ordered pair is the ordered pair that you apply your rule to. Okay? Then, add back to that the ordered pair of rotation / dilation. Okay? So so you start with an ordered pair, you subtract away something from it. Apply your rule, then add back in what you subtracted out. And that will give you your final result. Does that make sense? Okay. That's for rotations and dilations. Does that help? Any other questions on that assignment you guys want to talk about? Let's continue with the probability discussion that we were having yesterday. So we like to use probability to allow us to make decisions. Okay, we can't be guaranteed that through the use of probability that our decisions are going to be correct, but we can have high level of certainty that they're going to be correct. So, for instance, if we run through a study for dealing with like a medication, okay, trying to fix let's say a medication trying to fix heart disease, or let's just say high blood pressure, okay, we can, if I give that medicine to one person and one person only, and it fixes their blood pressure, does that give you, as somebody that needs their blood pressure adjusted, does that give you confidence that the medicine fixed to one person and only one person? No. But if we take, a study of, 5,000 people, and we find out in that study of 5,000 people that blood pressure medicine controlled the blood pressure of 4,800 of those people, then you, as a person that wants to have their blood pressure controlled through medicine, are you confident that medicine is going to work for you? If what we're saying is 96% people saw a control of blood pressure based on the medicine out of a large sample of people, then maybe that's going to give me hopes that medicine will work for me. Okay, if P&G finds that when they measure the volume out of one bottle of Tide that comes off the the assembly line, I won't call it an assembly line, but the line that they fill their bottles with, and it doesn't have exactly 32 ounces. Is that an indication that they need to stop that line and they need to go and completely tear down the machines and fix them? Probably not, right? One bad bottle out of, however many thousands they make in a day might not be a big deal. But if they've got 1,000 bottles out of the thousands that they make in a day, maybe we do have an issue. Does that make sense? So it allows us to make decisions. Anybody have, any of you drive? Got your own cars? But we're all getting to that point, right? Getting close to being able to drive. Let's say that two of you, let's say Robert and Lily have the exact same birthday, okay? Let's say that they are going to have the exact same car. They're going to have the exact same insurance policy, exact same company, all that kind of stuff, okay? Nothing's different between the two of them other than Lily's female, Robert's male, right? Which one of them is going to pay more in insurance? Why Robert? Huh? Okay, so he's 16-year-old. So probability shows that what happens with 16-year-old males when they drive? Okay, they're more reckless. They're more immature, right? Okay. So previous studies show that a insurance company, okay, do you guys understand how insurance works? So insurance works, so let's say that you go buy a $30,000 car, okay? You'll go get insurance on that. Basically what it means is that you're going to pay monthly charge, okay? They're going to, and usually people pay either monthly or like twice a year, okay, semi-annually. So they will charge you an amount so that they insure you, which basically means that, maybe you pay like $100 a month, okay, for them to insure you. In case you wreck or and ruin your car, damage your car, or even damage and ruin somebody else's car, okay, they will then pay out a claim. So let's say that I have a $30,000 car, I've bought it, I go get it insured, tomorrow I wreck it, okay? My insurance company is going to say, okay, what's the worth of that car? What's the value of that car? And they will then cut me a check for what they believe the value of that car is. Does that make sense? So that I can replace it, okay? Or they'll cut a check for if it's not totaled, the body shop or whatever to fix it, okay? Now you pay that premium, that insurance, and the idea is that most people pay it but never need a claim. Does that make sense? Okay, so you might be, I've paid insurance forever and I've never had to have a claim on a car, okay? I've been paying it since I was 16 years old, okay? But the time that I do wreck my car and I need that insurance, it's going to be nice, okay? I don't have to pay out of pocket $30,000 because I don't have it. Does that make sense? So basically what happens is that 16-year-old males have a higher chance of getting in a wreck because, one, they're less mature, they're more adventurous, okay? They like to go fast, right? So they put themselves in situations that 16-year-old ladies don't do, okay? And then the insurance company has to pay more money out to 16-year-old males than they do 16-year-old females, so that's why you then cover more of that cost as an insurance premium. What if it was Lily and Maddie? Let's say that they were this situation, the exact same car, exact same birthdays, okay, both females. We make the argument that they're going to both pay the same premium, right? Let's say Maddie's car is red and yours is the color of this cabinet, poop brown. Okay, who's going to pay a higher premium? Maddie. Why? Okay, so cars that are vibrant colors like red there's studies have been done on this. They are emotional. Okay, they create emotions and emotions to want to drive fast, specifically with cars. Does that make sense? You guys know why? This is not in regards to driving fast, but do you know why McDonald's and Burger King are like red and yellow? Yeah, those are colors that elicit an emotion of hunger. Okay, So it's a marketing thing, okay? But it's the same thing. That's why they make cars red. I mean, not too many. Well, there are, but there's not really too many. Like you guys seen Mr. Garland's Corvette? Like that red color. Don't see too many minivans that color, right? They make sports cars that color because you don't see a sports car this color, right? No. So there's marketing into that. But probabilities go into insurance. Probabilities go into the stock market. Probabilities go into, when I pay insurance, I pay house insurance. So in case my house either burns down, floods, or whatever, they will come back in and build my house for what it costs today. My insurance, let's say my insurance on my house compared to my a person that lives at the other end of the neighborhood. Let's say our houses were built in the same exact time period, roughly the same square footage, same ultimate loan value. My insurance is less than my neighbor's that lives maybe 10 houses down, because right across from my driveway is a fire hydrant. Across from their driveway is not a fire hydrant. The closest fire hydrant to them is next to my house. Does that make sense? So if there's a fire hydrant that's far away from a fire, less likely that fire is going to get put out, right? Okay. But I've got one right next to my house, so my insurance premium is less. Okay. My insurance agent, okay, he actually asks me every year when I call him and say, hey, is that fire hydrant still there? I'm like, yeah, Paul, I don't think they take those out. But that's what they do. So I get a reduction on it. Okay. I've got a swimming pool. Okay. I've got a diving board. My insurance is higher than somebody with a swimming pool without a diving board. Why? Yeah, so I need insurance to cover me based on somebody comes to my house, dives off my diving board, breaks their neck. Okay, I got to pay for that. That's homeowner insurance. Okay, somebody that doesn't have a diving board isn't going to have that issue, right? Okay, I don't know if they do it anymore, but sometimes they want to insure people when big trampolines came out. They want to insure people with those because people are breaking arms, necks, legs, that kind of stuff. Okay, so, but all of that is based on probability. Okay, do you guys ever hear like biologists or whatever say that we estimate that there are 300 black rhinos left in the wilderness or something like that? I don't even know if that's a thing. I think black rhinos are real, but I don't know if there's 300. Did they call like a black rhino meeting and they all show up and they count them? No. So what they do is they use probability. They go out and they tag so many rhinos that they see during some type of like study, and then they wait a little bit of time and they go back out and they tag black rhinos a second time. And of those black rhinos the second time that they tag, the hope is that there are some rhinos that had already had a tag. Does that make sense? So they can use those numbers together to model a population and say, okay, we tagged 3 rhinos, or let's say 30 rhinos the first time we went out. And then when the second time we went out, we tagged 50 rhinos, but of those 50, 12 of them had tags. So then we found 12 out of the original 30 that second time, right? So that 12 out of 30 can be used to determine how many are in the total population. That's called capture, recapture, that we use probability to do those things, okay? So probability is something that I think, I've told people this in the past, I tell my stats kids this, probability is a hard class, I think, at least in my opinion, in the classes that I've ever taken. That's the one that I probably had to work the hardest at, because some things aren't, sometimes the questions are abstract, but it's one of the aspects of mathematics that is probably most applicable to us. It's the most real world. It's the most impactful when you leave high school, and it's probably something you'll deal with the most after you leave high. I mean, you're going to deal with supplementary angles and alternate interior angles, stuff like that? Probably not. But you're going to deal with insurances, you're going to deal with stock markets and that kind of thing. When I go and when I invest in the stock market, my Edward Jones person asks me, how risk or what kind of risk are you willing to take? Okay, and basically they say, are you willing, if you were to take out and put $100,000 into the account today, are you okay with it being $80,000 tomorrow? Okay, so am I okay with a $20,000 loss overnight? Because on the flip side of that is, okay, if I lost $20,000, the flip side of it is that I could gain $20,000, right? So when we talk about risk and actuary analysis and stuff like that, it's all dealing with probability. Okay, the way the stock market works, people that are in the stock market for a short time usually lose a lot of money. But if you're in it for the long haul, and we talked about this yesterday at the end of the class, the longer a study is done, the more samples that get done. Okay, so I'm talking about stock market. The more days I'm involved in the stock market, the gains, through probability, the gains are always going to be greater than the losses. Does that make sense? Okay. Anybody gamble? Like to gamble? Okay, probably don't have jobs to get money to gamble yet, right? I hate gambling because I like my money. But people that gamble, they win and they lose, right? Okay, but most often net gains and losses, usually they lose more than they gain. Okay, casinos are based off of probability. Okay, games are developed where I might get Jagger hooked, okay, to play a game because he might play, let's say roulette, and he might win $100,000 on me that night. Now he's hooked for life. Okay, so he won $100,000 off me, but I've got another 1,000 people that are losing $200 on me in that night. Did their losses outweigh his one win collectively, right? So that's how games and casinos are built, is that they're going to pay out to individuals, but the masses are going to eventually cover those costs because the masses are going to lose more than what the individual payouts end up being. And it's all probability. Okay. This question here says a park has 538 trees. You choose 40 at random and determine that 25 are maple trees. It says, what is the experimental probability that a tree chosen at random is a maple tree? All right, so we don't want to go through and classify. We know that maybe this woods or park or whatever has 538 trees, but I don't want to go in and count every single one of them. Okay, so what we do, and kind of give you a visual of this. Let's say this is an overhead view of our park. We would not want to go to like this section of the park, that section of the park, and just start counting those trees, because this section of the park might be completely different than this section of the park, right? Okay, so what we'll do is develop some type of structure that would allow me to randomly say, okay, that part, that tree there, maple. I would go look at 40 random trees throughout the park. Does that make sense? Okay, I would look at those and say, of those 40, 25 of them are maple. And because I did this randomly, the idea then is that when I look at that tree right there, and I don't know what it is yet, it's got a 25 out of 40 chance of being maple. Does that make sense? Okay. So when it says what's the experimental probability, that's the probability that we gain from actually doing this experiment, from going through, counting the trees. Okay, this is the number of outcomes that are favorable and this is the number of possible outcomes. Okay, so we have 40 possible trees, and 25 of them favor being maple. So now, if we can use that, let's use that value. So now we're saying that out of every 40 trees, 25 of them are maple. So if I have 80 trees, 50 would be maple, right? If I had 400 trees, 250 of them would be maple. Is that okay with everybody? That's what we're doing here with this experimental probability. So if I've got 538 trees, 25 out of every 40 of those 538 are going to be maple. Does that make sense? So 25 out of 40 of those 538, and then we say of, that means multiplication. So that's why we multiply. We get 336 of these 538 trees are maple. Now that's an estimate, okay? It's the best estimate that we can gain from this experimental probability. Obviously, a tree can't be 25% maple, right? It's either maple or it's not maple, okay? So when we get fractions like that, we got to understand that these are estimates that we're using, okay, or that we're gaining, okay? I might actually go through, if I were to think about this, 336.25, and I get that result, and then actually go through and look at every one of those 538 trees, we might not get 336, okay? But we'll probably get something pretty close to 336. Does that make sense? Okay. Now, with probability, I'm not saying that we will. Okay, we could go through and count and only get 100. But we're saying that based on this experimental probability, that is probably the most likely answer. Does that make sense? Theoretical probability. So yesterday we talked about experimental probability, and that's actually going through and doing an experiment, like flipping a coin or rolling a dice, okay? But there is theoretical probability as well, okay? So if I roll this dice, okay, there's 6 numbers on it, right? If I roll it one time, I get a 1, okay? I could roll it 3 more times and get a 1 to show up every one of those times, right? Okay? That's not what we would expect to happen. Okay, if I roll this 6 times, I would expect 1 to show up once, 2 to show up once, 3 to show up once, 4 to show up once, 5 to show up once, 6 to show up once, right? 1 time, 1 face for every roll, okay? That's what we call theoretical probability, okay? Experimental is actually doing it and knowing that I'm not always going to get a 1 to show up 1/6 of the time. I'm not going to get 2 to show up 1/6 of the time, okay? Theoretical probability says that your likelihood of an event is based on mathematical reasoning, mathematical formulas, mathematical proofs, okay? Mathematical reasoning says if I flip a coin, because there's 2 outcomes, half the time the outcome should be heads, half the time the outcome should be tails. Rolling a dice, because there's 6 outcomes, and because the shape is not, so if I look at a cube, like there's nothing about this cube that is going to skew like the 2 to show up more than the 3. Does that make sense? So each face is equally likely to occur showing up as any other face. So they're equally likely to occur, and that's important to think about. But we would expect theoretically that if I roll this 600 times, that 100 heads, or sorry, 100 ones, 100 twos, 100 threes, 100 fours, 100 fives, and 100 sixes would show up. Does that make sense? Okay. But we know that if we roll it 6 times, we don't really get the 1 to show up once, the 2 to show up once, the 3 to show up once, and that kind of thing. We might get 4 threes, a 1, and a 5. Okay, that's just the way probability works on a short sample space. Yeah. Yeah. Oh, okay. Yeah. Yesterday we were talking about the situation where we could flip a coin 10 times and not realize 5 heads, 5 tails. Okay, what I just built here is basically taking this, takes a random number between 0 to, I don't want to say between 0 and 1, it just takes a random number 0 or 1, and it just chooses randomly which one to show us here. Okay, and then if it's a 1, it calls it a head. If it's a 0, it calls it a tails. So this is the idea of flipping a coin without physically flipping it. Does it make sense? So what we've done here was we flipped the coin 10 times. We got 9 heads and 1 tail. Okay? That's experimental probability. We should expect 5 to 5, right? Okay? But we don't. We get 9 and 1. Now, I don't see if there's I forget where it's at, but there's a button here to recalculate. Calculation options. Okay, so I can just recalculate these. So now I flipped it 10 times, got 8 and 2. Flipped it 10 times, got 4 and 6. That's closer to 5 and 5, right? But so now I've flipped it maybe, collectively like maybe 10 times now. So I've done 10 flips 10 times. That's 100 coin flips, right? So if I were to take this thing and drag it out to 100, and then go back and look at these, 44 and 56, okay, that's closer to 50-50, right? That's closer to 50-50 than 8 and 2 or 9 and 1 or 7 and 3. Those are going to be, so I'm not going to get, I don't want to say I'm 100% not going to, but I'm probably not going to get like 30 and 70. Does that make sense? Now, it could happen. Okay, you can flip a coin at your seat and get 30 and 70, but most of these are coming between, 55, 45, okay, 57, 43, right? Okay. Now, if I were to, so this is, let's say I do this, I flip these 100 times, and I collect those 100 flips. So 100 times 100 is 10,000, right? So let's say that I don't know how long this will take to drag this out. If I drag this out beyond, it's easier on, that's why I was trying to get Google Sheets open. I got one built. It's easier to get to drag down to like 100,000. But we'll go to maybe 1,000 here. Okay, so it fills those formulas in there. So now I'm just going to take and look at the decimal version of these results. Okay, and what we're going to find out is that when we recalculate this, okay, those numbers are closer to 50-50, 0.5 and 0.5, than they were when we were doing it with 10. Does that make sense? Okay. And the idea is now 1,000, even though 1,000 is a lot, 1,000 is a very small sample spot size in comparison to what it could become. Let's say I took 1,000. Let's say each one of you flipped a coin 1,000 times and did your recordings of how many heads and how many tails you got. Then we added those all together. Okay, so now we have like 14,000. Does that make sense? Okay. The larger the sample size, the more that our heads and tails are going to become, as a fraction, 50-50, 0.5, 0.5, okay? Experimental probability says you might not get there, okay, on a small scale, okay? 10 flips, we got 9 and 1, okay, or 8 and 2. But if I go 100,000 flips, it will be 50-50. So the idea is that experimental probability and theoretical probability are different on a small scale, a small sample size. But the more samples that we get, the more that we do the experiment, our experimental probability starts to converge or becomes the same as our theoretical probability. Does that make sense? And because of that relationship there is why all statistics works. Okay, it's why when we talk about car insurance, when we talk about medical insurance, we talk about medical studies and those types of things. The more people in your sample, the more reliable the results are, because the results are going to be more in tune with what theoretically should happen if the sample size gets larger. Does that make sense? Okay, I mean that's the number one thing about probability that we need to understand, so that we can realize, why is it that probability gets used to allow us to make decisions down the road. Okay. When we do theoretical probability, a lot of times there's scenarios that we're interested in, like rolling dice, flipping coins, picking cards out of a deck of cards. You need to know what the sample space looks like. Okay. So that's the one thing that we try to find first. Okay. When they're asking you to roll dice or number cubes, a lot of times you're going to, especially if you're dealing with 2 dice or something like that, you're going to want to create this sample space here. Okay? The question is, what is the probability of rolling numbers that add to 7 when rolling 2 standard number cubes? They call them number cubes because a lot of schools forbid gambling. right? In our handbook says we're not allowed to play cards, right? Because that's obviously a gambling situation, I guess. So they, instead of calling them dice, because then that goes back to gambling or dambling, so they call them number cubes, but it's a dice. So we want to add to 7. All right. So you've got 2 dice. I don't know if I've got another. There we go. Got these 2 dice right here. Okay. So if I throw them and they didn't add to 7, they add to 11. Okay. So I don't count that. Okay. So I have to figure out, okay, which outcomes are favorable to adding to 7. Well, 3. Let's say I start with 1. There's 1. Okay. And then this one has to be a 6, right? So that's favorable. So that 1 outcome there. What if I go 2 and 5? There's another favorable outcome, right? So now I've got 2 favorable outcomes. 3 and 4, correct? So there's 3 favorable outcomes. Could I go 4 and 3? It's another favorable outcome, right? Okay, because there could be a 4 on this one and a 3 on this one versus the 4 on this one and the 3 on that one. Can I go 5 on this one and 2 on this one? Does that make sense? Okay. So we have to figure out how many of those different combinations are going to add to 7. But then we also have to find the number of combinations that don't add to 7. So the best way of doing this is to figure out the sample space, okay, because remember we want favorable outcomes to possible outcomes. Okay. This is the first dice that we're going to roll, and this is the second dice that we're going to roll. Okay. On the first dice, you could get a 1, and on the second dice, you could get a 1. On the first dice, you get a 2, and on the second dice, you could get a 1. So these are the things that you could, there's a systematic approach to finding all the different outcomes that you could get, right? So the first dice could be a 1 paired with anything from the second dice. The first dice could be a 2 paired with anything from the second dice. It could be a 3 paired with anything from the second dice. Does that make sense to everybody? So we have a sample space of how many possible different outcomes are there here. Yeah, there's 36 different outcomes. How many of those outcomes add to 7? 6 of them add to 7, right? 6 out of 36 reduces to 1/6. So when I roll 2 dice, there is a 1/6 chance that I am going to get a 7. Does that make sense? Okay. You know, what's the probability? You guys play like I don't know if they used to. They play games where if you roll ones were called snake eyes, right? You guys ever heard that before? Okay, and then there's whatever game you're playing there. If you roll double 1s or you roll double 6s, I think Monopoly. If you roll double 6s, did something bad happen to you? I can't remember. Or something good happened, something like that, because these are rare. Rolling a double 1 and rolling a double 6. If I roll a double 1, okay, that's only 1 out of 36 chances that's going to happen, right? Okay. If I roll double 6, there's only a 1 out of 36 chance for that happening. Okay. Now, if the rules were you just need to roll a double number, so a 1-1, a 2-2, a 3-3, a 4-4, a 5-5, a 6-6, that would be 6 out of 36. Does that make sense? Okay. So this is what we refer to as the sample space. Okay. There are different scenarios asked for different sample spaces. You guys talk about in the past, you ever deal with questions that you've got a bag and there's blue marbles and black marbles and red marbles, and you close your eyes and pick out a marble. What's the probability that it's red? Okay. Well, I need to know how many marbles are in there to begin with. That's my sample space. Okay. And then I need to know how many of them are red, because then when I compare the red ones to my sample space, that's the probability of picking out a red one. Okay. But then we start doing things that are a little bit more complex and say, okay, if you've got red marbles, blue marbles, and black marbles, what's the probability of reaching in and not picking a red one? Well, not picking a red one would be picking a blue one or a black one, right? Okay. So there's a couple different ways we could think about it. Now and this is where we start talking about, we talk about, it's called a complement of an event. Okay? We've seen the word complement in mathematics already, and geometry this year. If I have two angles that add to 90, they're called what to one another? Complementary. Okay? Because if I tell you one of them 60, you know how to find the other one, right? You take the total, which is 90, and subtract 60, which is the one that you know, and you get the complement of 30, right? The word complement collectively across mathematics means take the whole minus the one you know, and you get the other one. Okay? So if I know that, what's the probability of rolling a 1 is 1/6. Then the probability of not rolling a 1 would be 5/6, right? It'd be the probability of getting a number minus the just a number to show up, 1 through 6, minus the probability of getting a 1 to show up. Okay? So what we do when we go with complements, okay, says consists of all the possible outcomes in the sample space that are not part of the event. And what that means is that the probability of a complement is equal to 1 minus the probability of the event. Okay? So let's say I want to say what's the probability of not adding to 7? That would be 1 minus the probability of adding to 7. Does that make sense? Okay. So adding to 7 was 1/6. So not adding to 7 would be 1 minus that, right? Okay, so 5/6. Now think about this. Would you agree that these here in red are all the ones that don't add to 7? If you go through and count those red ones, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 of them on this side. So you have 15 on this side. So you got 30 out of 36 that are not adding to 7, right? What's 30 out of 36 reduced to? 5/6. Isn't that easier to do? It was easier to count the ones that were adding to 7 and then do 1 minus that, okay, to find the ones that don't add to 7. So complements are 1 minus the probability. If I say that it's a probability, what did they say, like 90% chance that we're going to get snow today, tomorrow? So what's the probability that it doesn't snow? 10%. Okay, it's 1 minus the event is going to equal the probability of not that event. Okay, so that's the complement concept or complement idea. So here we'll just do an example real quick with this. It says a jar contains 10 marbles, 8 green marbles, 5 blue marbles, 6 white marbles. What's probability a random selected marble is not green? Okay, so you could do this. So not green, we can do it 2 different ways. Probability. The way that we use the word not, they'll a lot of times do this. I'll put a little tilde here and then say green. Okay. I'm going to rewrite that as probability not green just so we see the different notations that can be used. Okay. Well, probability of not green, doesn't that mean that could be the probability of red? Then plus the probability of blue, plus then the probability of white. Does that make sense? That would be not green, correct? So how many are red? 10 out of, so we got 18, 23, we got 29. Okay. How many are blue? 5, so 5 out of 29. How many are white? 6 out of 29. So that gives me, what, 21 out of 29. That would be the probability of not green, correct? Now, think about this math here. Probability of not green. Let's say that is the probability of 1 minus the probability of being green. How many are green? 8 out of 29, right? This 1 can be written as 29 over 29. What's 29 over 29 minus 8 over 29? 21 over 29. Is that the same answer? Was this less mathematical work to get the answer using the complement rule? Okay. So that's the idea that the complement rule will allow us to do. It will allow it, and this is something that we use all the time when we get to probability statistics, okay? When we get to that course. The complement rule, its point or its intention is to alleviate a lot of calculations. And sometimes it's a workaround to get a result when there's a calculation that is impossible to conduct. Okay? Maybe we'll see some examples of that within the next couple of days. We'll stop there for today. Again, no new homework yet. They were?